Okay, so today we begin an important topic called ergodic processes, or let me put it this way, ergodicity. Now, you see, suppose we are given a random process x t and we want to find out we want to determine its statistics, say various moments, for that matter say mean. Now, how to estimate the mean? That is, suppose you want to find out the mean at some point of time t prime. What will you do? So, this is what is this? By definition, this is this. Okay. Now, how will you estimate this? So, naturally, you have to conduct several experiments. With every experiment, you will get a wave from x t. So, measure the sample x t prime, again conduct the experiment again get another wave from, again measure the sample at t prime, so and so. And if you conduct this experiment several times, say capital N number of times, then add all the sample values and then divide by capital N. So, that will be a sample average, and if capital N is very large, it tends to infinity, that will become a better and better, and finally, the correct estimate for is mu. That is, we do what is called ensemble average. That is, maybe x t s I, where x t prime s I. S I stands for the particular experimental outcome, okay, s I. For that outcome, the corresponding function is x t comma s I. That is, for the experimental outcome s I, you have got a waveform which is x within bracket t comma s I. So, there I am measuring the sample value at a point of time t prime, and next again I conduct the experiment. So, I get another experimental outcome. For that also I have another waveform. So, I measure the same sample value, I measure the sample value at the same point of time t prime, so on and so forth. So, I add all the sample values over the various experimental outcomes, that is over the ensemble, and then divide by capital N. So, that is an ensemble average, and if n is very large, if I give n tends to infinity, this right hand side tends to the actual statistical mean. This we know. Problem is, in real life we may not have the time to have so many experimental observations just to calculate one mean, because everything, most of the operations that we do in our engineering, they are done in real time. So, you won't get time to conduct the experiment or to measure the wave from time and again, so maybe 100 times or 200 times, and then estimate mean and then proceed for your next job. So, ergodicity is a concept which helps us a lot in this. Now, suppose you got only one waveform. Okay, suppose you got only one waveform for a particular outcome S. So, this for a particular outcome S, or for any outcome S, you got a one waveform. Suppose I do some kind of a time average of that, and you call it, give it a name mu t. Okay. Question is, can this mu t for a very large value of this capital T, you see what is happening is I am integrating the function and then dividing by the length of the, this duration, that is 1 by 2 t, that is 2 t. So, it is an average, time average. I am integrating it and then dividing by the total time period that we have here, minus t to t, that is 2 t. Is this time average, will this time average give me some idea, or maybe exactly this statistical average, that is the actual mean? Now, before even we consider such a possibility, you have to see one thing, that if I really carry out this time average, I get a constant which is independent of time. It is a constant. That means, for this to work, for this to be valid, this process, the mean of the process should not depend on the particular time instant t prime where you are measuring. That means, it should be constant at all point of time, which means it should be stationary in mean. That is, this mu t prime should be just mu. It should not matter whether what t prime you have chosen, because if I have to have mu is equal to mu capital T for very large t, or maybe as t tends to infinity, that is, the question that I was to pose is, can we have a situation where mu t tends to mu as limit t tends to infinity? That is, if I average over a very large period, do I get mu t closer and closer to mu? Now, for this to work, first you see this integral, as I said, this is independent of the time, you get a net constant quantity. So, for this to be equal here, that is, the process should have mean constant, that is, it should not depend on the time instant t prime where it is measured, which equivalent means the process should be stationary in mean. Suppose it is so. Suppose the given process is the process xt is given to be stationary in mean. Even then this question lies, that if mu t is equal to given to be question limit t tends to infinity mu t is it equal to mu? This is the question. Is limit mu t where t tends to infinity is equal to mu? Okay, this is the question. Now, if that happens, okay, then I will say that the process is ergodic in mean, if that happens. Okay, but before that, what we are doing here is we are doing some kind of a time average. Okay. So, a mathematical question arises whether this limit exists at all or not. Okay, whether this limit exists at all or not, that is this limit. After all, limit mu t t tends to infinity means what? Limit t tends to infinity does it exist? Answer is yes. It was proved by one famous statistician called named Barkov. He said that this exists provided x t s is stationary and expected value of mod x t, if it is stationary, it does not depend on s, E of mod x t, that should be finite. If that happens, this limit exists. It is just for a mathematical this thing, correct, I mean to be mathematically correct, or just for mathematical interest we are writing this. We will always assume that this exists, these conditions are satisfied, so we can happily take the limit. But when you write a mathematical statement like this, you should provide the condition under which it is true. That is why you gave this condition. This was obtained by Barkov. The process should be stationary and E of mod x t should be finite. And obviously, there is nothing big deal about it. It means that the mean should be finite. If that be so, then this limit exists. So, we can happily take the limit. This was proved by somebody. But then that brings us to that initial question, that now okay, the limit exists. Does the limit give us actual mu? That is the actual statistical average, the expected value of x t. That leads to this concept of ergodicity. And again, when I say ergodic, it is more general. It is not only restricted to mean. In fact, it is restricted to any kind of time average. For that matter, say we will be dealing with this also after some time. Suppose you are finding out correlation. Okay, what you do to estimate this? You carry out this product over ensemble. I mean, for each sample function, you carry out this product and average over the ensemble. That will give you an idea of this, an estimate of this, and if total number of observations over which it is average is large and large, it will be a very good estimate of this correlation. But again, that question comes that does it become equal to this? That is, if I carry out instead of taking the expectation over the ensemble, if I do the expectation or this averaging, expectation is same as averaging over time, this quantity, and limit tend to infinity. Does this give us this? Okay. And here it is second moment. I can take third moment also, fourth moment also, and all that. So, essentially, if this time average gives rise to ensemble average, then we say the process is ergodic. And when I say ergodic, it applies to all the moments, not just for mean or correlation, it applies to all the moments. That is, to evaluate all the moments, instead of carrying out an ensemble average, you can carry out a time average like this. If that is true, then the process is called ergodic. Now, if the process is ergodic, that means that just by time average, I can determine all the moments just from given one particular sample function. I can carry out this time average and get all the moments, and if I know all the moments, I know the entire probability density and distribution. So, I know the full statistical characterization of the process. So, that means one sample function should be enough to obtain the statistical characterization of the process, that is obtain all the moments or equivalently probability density or distribution. Okay. Now, I consider first mean ergodic process, that is processes which are ergodic say only in mean to start with. Here actual statistical average or expectation which you obtain by taking ensemble average, and if the number of terms in that average, if number of times you average it, if number of times you observe it before averaging, if that is large and large, then that average becomes actually same as the actual statistical average or expected value of the xt. And I am assuming the process to be stationary in mean, obviously because the region has been told already that if I talk of ergodicity, it has to be stationary. So, suppose stationary process, at least a process which is stationary, a process which is stationary at least in the mean, that is given to me, and the actual mean or actual expectation is this, which you can obtain by ensemble average, provided you take very large number of observations. Question is, if I now form this quantity mu t, then it is mean ergodic if is equal to mu. Okay. Now, what should be the condition? What should be the condition on the process? What kind of process it should be? What should be its characteristics so that this is satisfied? We now investigate that. You see, given any x t, if you carry out just this integral from minus t to t and this divided by 1 by 2 t and you get mu t. Naturally, mu t is a random variable, because next time you have another observation for the process, say another x t, you carry out the integration, you get another value of mu t, so on and so forth. So, mu t is a random variable. What is the mean of mu t? U of mu t, clearly you push the expectation operator inside the integral, because expectation is a linear operator, E working on x t, and E x t, because of stationarity of x t is constant, that is mu, again mu comes out of the integral. So, integral gives rise to 2 t. So, mu into 2 t divided by 2 t, which is equal to mu. That means, this mu t is a random variable whose mean is mu. Okay. But that is not enough. It is true that whenever you observe this mu t for any choice of capital T, not necessarily infinity, its expected value would be mu, but I am not interested only in that. I want that mu t should become equal to mu. Okay. Now, here one thing I mentioned, that since mu t is a random variable and I am taking a limit, I must tell you in what sense is the limit carried out. Now, here it is mean square sense, that is the difference between mu t and actual mu. Mu is constant, mu t is a random variable, mu t minus mu, that difference, that is an error. If you take the variance of that, that is expected value of mu t minus mu square, that should become less as capital T becomes high. So, that should tend to 0. In that sense, I am writing this limit expression, that okay, mu t approaches mu in the mean square sense as t tends to infinity. So far, I have only got that for any choice of capital T, mean of this random variable mu t is mu. But for this ergodicity in mean, I must have this satisfied, that if I call it sigma t square, I am taking all real case. So, there is no point in putting a mod, because I am taking a square which is same as What is mu minus mu t by the way? Let us do this thing separately here. Mu minus mu t we can always write as, or maybe it is better that I put mu t minus mu. It does not matter though, because it is a square. Mu t minus mu. What is mu t minus mu? Mu t I know this, minus t to t x t, and I can also write x t minus mu d t. Obviously, because if you take the mu part, mu comes out, integral gives you 2t by 2t cancels, so you get back again mu. Okay. Now, these variants, there is what? Mu t minus mu is equal to this. So, I have to take the square. So, there will be a double integral and expectation there. Okay. So, if you take the double integral, one integral will be with respect to say t 1, because this is t is the local parameter, local variable of integration. So, you take t to be t 1 in one of the integral. Next time when you because this is a square. So, mu t minus mu times mu t minus mu. In the first mu t minus mu, you will replace that mu t minus mu by this expression, but take t to be t 1 as the variable of integration. In the next case, you take t to be t 2. So, double integral with respect to t 1 and t 2, and then push the expectation operator inside the double integral. Okay. That is what you will get here. That is and there will be a 1 because 1 by 2 t. So, that will give rise to a 1 by 4 t square, that is an important term. So, I should not ignore that. One by 4 t square double integral, and now instead of working out step by step, I think we are now sufficiently mature to see what result we will get. If you have x t 1 minus mu and again x t 2 minus mu, and you carry out this and then apply the expectation operator on this product of these two terms, what you will get is simply the covariance of the process x t when measured between the two time indices t 1 and t 2. I have assumed the process to be stationary in mean, but not necessarily stationary in correlation also, that is not necessarily second order stationary also. That is why I will not say that covariance is not a function of t 1 or t 2, but is a function of t 2 minus t 1. No, not still, not yet. It is stationary in mean, that much I am using. Okay. So, I repeat again, or maybe I write down in case you have got terms like this: x t 1 minus mu, x t 2 minus mu, and d t 1, d t 2. Now, this clearly gives you the covariance of the process x when measured between the two time indices t 1 and t 2, and is not necessarily a function of the lag t 2 minus t 1 or t 1 minus t 2, because I am not assuming the process to be stationary in covariance or correlation yet. Okay. In that case, this simply becomes equal to 1 by 4 t square one by 4 t square C is the covariance T 1 T 2 d T 1 d T 2. Now, if this quantity tends to 0 as capital T tends to infinity, that means this error variance sigma t square is becoming 0 in the mean square sense, which means mu t is approaching mu in the mean square sense as t tends to infinity. If that happens, then I will say this process is ergodic in mean. That means the condition for ergodicity in mean is simply this. This fact, thus limit t tends to infinity, this integral 1 by 4 t square c t 1 t 2 dt 1 dt 2, this should what? This should tend to 0. If that happens, then the process is ergodic in mean. The process is ergodic in mean. You can take an example. Suppose x t is given to be some mu plus z t, where z t is a 0 mean random process, mu is constant, z t is a 0 mean random process. What is expected value of x t then? Mu, because E of z t is 0, and therefore x t is stationary in mean, because the mean, that is expected value of x t, is constant, that is mu independent of t. So, that first condition is satisfied, that is stationary in mean, and it is given also that z t has a correlation, that is the correlation of z t is given to be correlation or covariance, because z t is 0 means, so correlation covariance means the same. So, C z z, if you call it t 1 comma t 2 is is a White sequence. So, it is given to be some function q t 1 into delta t 1 minus t 2. So, that means if t 1 and t 2 are same, then only it has got a value, but that value is not independent of t. At t 1 it has a value q t 1. So, if t 1 changes, this value changes. So, variance changes from point to point, but the process is uncorrelated, that is between t 1 and t 2 there is no correlation or no covariance, it is 0 mean here. So, no correlation covariance means the same. So, that kind of thing. Here if the process x t is to be ergodic in mean, what is the condition? I simply apply this condition here, that is 1 by 4 t square, if we apply minus t to t. Now, C t 1 t 2, if you put here, q t 1 is the integral outside, because t 1 I will take to be the variable of integration for the outer integral, and inner integral will have delta t 1 minus t 2 with respect to t 2. So, that integral will have value only 1, it is a delta function, t 1 is constant within that, that is it will have things like this, q t 1 d t 2, and this integral is 1, the property of delta function, this is 1, okay, and we basically get this part. So, I am not, I can even eliminate this. What you get? In fact, you can even ignore this t 1, now call it t. This should be, as this should tend to 0. Okay. This should tend to 0. This q t variance integrated divided by 1 by 4 t square as t tends to infinity, so it should be 0. We now take another important case, special case. X t is given to be WSS. If x t is WSS, then that means instead of C t 1 T2 is to be a function of C T1 minus T2, and I should have this D2 should tend to 0 as t tends to infinity. Okay, this is the thing. What does it imply? Let us see. Let us see what is this, how to carry out the integral. Maybe I am not sure, we have done this exercise earlier. This is double integral within this box. This function is to be integrated within this box. The what function? C T1 minus T2. So, this is such a function which neither depends on T1 or T2, but depends on T1 minus T2. Okay, so, if T1 minus T2 is constant in a region or in a segment of this or in a part of this square, then C T1 minus T2 is a constant over that segment. So, therefore, if I consider the straight lines like this, T1 minus T2 equal to say tau. Okay, this axis is T1, this is say T2, T1 minus T2 tau. To start with, suppose I take tau to be say here, tau. What is the slope of this? Slope is 45 degree, okay, 1, this curve. If it is tau, it will go like this. If it is tau, okay. And so, over this line, this function has same value, because over this line T1 minus T2 is constant tau. So, I have a constant value C tau over all the point from here to here, okay, from here to here, or all the point within the square I have got constant value. And now, when I take a line close to it, T1 minus T2 is equal to tau plus d tau. That means, I will have one more line, if it is tau plus d tau. Okay. So, I will take this area, over this area, since d tau is infinitesimally small, over this area the function c has a constant value, that is c tau. So, what is the integral over this infinitesimal segment? C tau times this area, and then I will sum up by this integral to include the entire square. What is this area? Firstly, you can see one thing from elementary geometry, the slope is 1. If you had taken this line, this also has slope 1, that means all these lines are parallel, right. But if you in this triangle, this side is equal to this side, therefore, in this triangle also this half is equal to this half, or in this triangle also this half is equal to this half, okay, from similarity of triangles. Okay. So, I am to find out this shaded area, what I will do? I will take the bigger triangle, find out its area, subtract the area of the inner triangle, this smaller triangle. Okay. Now, to find out the area of this triangle is enough to find out one of the side, because it is isosceles, right angled isosceles, as I told. So, you find out this. Now, look at this straight line T1 minus T2 equal to tau, this straight line. When T1 equal to capital T, then this is T minus tau, this is T minus tau, and this is T. So, this length is 2 T minus tau, and therefore, this length is 2 T minus tau. So, I have got half 2 T minus tau square, this is the area, half 2 T minus tau square. And how about the inner triangle? Instead of T minus tau, it is T minus tau minus dt. So, it will give rise to d tau, okay, square. So, obviously, you get half 4t minus 2 tau minus d tau and d tau, and this d tau you can ignore, because d tau into d tau, that will be negligible, and this 2 cancels here. So, you get 2 t minus tau d tau, that is the area. Okay. If on the other hand your line was passing on this side, here tau was taken to be positive. If your line, and mind you, tau will go up to 2 t, because this is the limiting case. This is the limiting case of the straight line, and this is 2 t, and from here it will go up to minus 2 t. So, tau will go from 2 t to minus 2 t. I took positive tau, let us take negative tau also. Let us take negative tau. So, here tau. So, tau is actually negative, okay. And if we draw a line and another line through this tau plus d tau, so I have to find out this area. So, I will find out this bigger triangle and then minus this inner triangle, these two areas. I will take the area of the bigger outer triangle or bigger one and minus the area of the inner one, that will give the shaded area. Now, what is this point? This point is, you look at the equation, T 1 minus T 2 is tau. Tau could be negative here, I agree. So, what is this point? Here T 1 is minus T, minus capital T. So, that means T 2 is minus capital T minus tau. Okay. So, what is its length? This part is isosceles. Okay, that comes because the slope is 1. So, what is this length? This length is simply, let us do this way, this is length t and this is length mod tau, because tau is negative. So, this length is not tau, but mod of tau. So, total length is like this length, this point is minus t, but actual length is capital T. This is tau, but actual length is mod tau. So, this length is t minus tau. So, this is t minus mod tau. So, this is t minus mod tau, add to that another capital T. So, 2 t minus mod tau here. Okay. In the previous case 2 t minus tau, tau was positive. So, there also I can put a mod does not do any harm, and here 2 t minus mod tau, and in other case 2 t minus mod tau minus d tau. Okay. So, even here if you calculate the same way, you will get this same figure 2 t minus mod tau d tau. Okay. So, tau will go from minus t to minus 2 t t capital 2 t, minus 2 t to plus 2 t. Okay. That means, what is the integral? Now, I think it is very clear to you. What is the integral? that integral is 1 by 4 t square with respect to tau now. So, minus 2 t to 2 t c tau into 2 t minus mod tau d tau. You can take one 2 t common here because there is a style. So, you write 1 by 2 t So, if this quantity, if this tends to 0 as t tends to infinity, then mean ergodic. Okay. So, this is a condition, but we can have some sufficient conditions, a sufficient condition for this. So, we go to the next page, we rewrite what we wrote, that is what is the condition? Condition was 1 by 2 t, I am rewriting only, nothing else. For my reference, I am rewriting here c tau 1 minus mod tau divided by 2 t d tau. This should become, this should tend to 0 as t tends to infinity. This should tend to 0. This is the condition for ergodicity mean for a WSS process. Now, sufficient condition, that is, if this is satisfied, what is meant by sufficient condition? Stronger conditions, that if they are satisfied, this will always be, this also will be satisfied. It is not that, it is not necessary. What is sufficient condition? It is some condition which, if satisfied, would automatically imply that this above condition here also satisfied. But that sufficient condition may not always be necessary, so it may be stronger, but still we go for them because it makes life easier. So, here you see one thing, look at this integral, tau becomes positive and negative both, but mod tau remains positive, and mod tau by 2 t, it is never exceeding 1, because tau's range is 2 t and minus 2 t, minus 2 t to 2 t. So, mod tau by 2 t is one factor whose value is always less than or equal to 1. So, 1 minus mod of tau by 2 t, this is a factor, this is a term which lies between 0 and 1, but positive, always positive but 0 and 1. So, it is a fraction, that time c tau. So, obviously, this integral is what? You can write that is above integral c tau can be positive and negative both. So, therefore, if I instead of take a c tau, I take mod c tau. So, always I get positive. So, that means the net integral and this factor is positive, this is never negative. For any tau, this 1 minus mod tau by 2 t, it is always, this is important, it is always non-negative lying between 0 to 1, but c tau can be negative. So, instead of c tau, I put a mod c tau. So, obviously, net integral will be higher because down there is no negative value. This term, this phrase is positive or non-negative, the other term c tau, if I take only its mod value. So, obviously, the product is always positive. So, integral becomes larger than what we have here. So, that means this integral becomes less than and now, as I told you, this factor is always 1 minus mod tau by 2 t, so less than 1. So, if I remove this, integral becomes still higher because earlier I was multiplying this mod c tau by some number which is less than 1, say. So, if that less than 1 factor is removed, that is replaced by 1, obviously the total product value goes up. So, obviously the integral becomes higher. So, that means this becomes less than equal to, say, if you want to be very correct. So, if the right hand side now is such function that it tends to 0 as capital T tends to infinity, then obviously left hand side also should tend to 0, because this is always less than equal to this. Okay. Remember one thing, that left hand side is less than equal to this right hand side. So, if right hand side tends to 0 as tau tends to infinity, what happens to the left hand side? Now, left hand side, you remember we started with, it was a variance function. So, it is lower bounded by 0, this is important, it can never be negative. So, left hand side can never be negative, it is lower bounded by 0 on one hand, but is again upper bounded by a function which is becoming 0. That means, this left hand side has no other option but to become 0 as t tends to infinity. Do you understand this? The left hand side function, if you if you look at the early part of this today's lecture, this was nothing but a variance function, and variance function is what? That was lower bounded by 0. Okay, and this is upper bounded by this function, but this function, if it tends to 0 as t tends to infinity, obviously this left hand side has to become 0. Okay. There is another condition which is according to me more useful, another equivalent condition. This condition was 1 by 2 t should tend to 0 as t tends to infinity. But I have got another condition. If you forget this, if this is given to be that C0 is always real, so no point, and this is suppose given to be number 1 finite. There is variance is finite, there is nothing big deal. Okay, variance is that instantaneous AC power, you can say that expected AC power, there is you have a mean, around the mean there is a fluctuation, that fluctuating part. Okay, what power has it has this C0. Obviously, this is this, I mean, for all real processes this cannot be infinity. So, it is finite. Suppose this is true, and other thing is C tau, if it is given that it is greater than 0, it tends to 0 as tau tends to infinity. That is, as tau becomes larger and larger, covariance between the respective samples situated at a gap of tau becomes less and less. That is, samples situated far away from each other, they become uncorrelated or close to uncorrelated. This is always true. I mean, this is true in most of the practical processes, because the samples which are nearby or adjacent, they are only correlated. If you go far away, if they are far away from each other, then the degree of correlation between them is less and less. Okay. In that case, also this is also then a sufficient condition. Now, how to prove that? We have already seen this integral d tau, this we have seen is less than this. This you have seen just now. Okay. Now, you told me, so firstly capital T will become large and large. Now, you told me that as tau becomes more and more, C tau tends to 0. That is one of the condition. That means, given any epsilon greater than 0, however small, it can be very small, but positive. You can find out an A, so that maybe this is the time axis 0, your 2t here, minus 2t here, A is somewhere here. See. It could be to the right side, but then capital T is becoming higher and higher, is tending to infinity. So, naturally, I can always take 2t to be to the right of A to be more general. Okay. And you can find out A, so that to the right of A, the correlation, that is, if you take tau to be, this is tau axis, if you take tau to be, that is the lag, tau to be greater than A, correlation is almost 0, that is, it is less than epsilon. Give me any epsilon, I can always find out some A, there is some lag, however large, beyond which the correlation has come down to be very small, that is less than epsilon. Okay, that is one of the conditions. So, that means, mathematically speaking, you can find out A, so that mod C tau less than epsilon for tau mod tau greater than A. That is, tau can be to the right hand side also or this side also. Okay. If that be the case, and this right hand side integral here I can write as summation of two integrals, one from minus A to A, C tau d tau, another, that is, once you integrate over this period and then integrate over the remaining period, this part and this part. That is same stuff, but tau greater than alpha A less than 2t. This is the range. Okay, if that be, now look at this integral. Now, we know, we have seen earlier that Cauchy inequality, that C tau is always less than equal to C 0. Okay, C tau is always less than equal to C 0. Its mod is always less than equal to C 0. C 0 is positive, so I am not putting any non-negative, so I am not putting any mod. So, that means, if this on the right hand side the first integral, this is always less than equal to twice A into C 0, and this other integral since C tau is less than epsilon, this other integral is equal to what? How much area? From A to 2t and minus A to 2t, okay, that much area. Yeah, that is very simple. So, the first integral here, I am starting from this point. Okay. Just to see the continuity, this is less than the first integral is less than equal to, it should be less than equal to, but I will make it less than, because the other term, for the other term it will be less than. So, it is to integral twice a times C 0, because mod C tau is less than C 0 by the Cauchy-Schwarz inequality. So, if you put that within this first integral on the right hand side and C 0 comes out of the integral, this is true. And the second one, within this zone, I have said within this zone from a to 2t or minus a to minus 2t, the correlation, this covariance fraction magnitude has already fallen below epsilon. So, obviously, this net integral will be what is less than 2t times, if you really take up to 0 to 2t, okay, it's, and on this side also 0 to 2t, it is less than 4 epsilon t. This integral, though integral is taken not from 0 to 2t, but of a fraction of it, just a to 2t or minus a to minus 2t. Even if it were taken from 0 to 2t, it still would have been less than, on the right hand side twice epsilon into twice 2t, on the left hand side also epsilon twice 2t. So, 4 epsilon t. Okay. So, if you now divide by 2t, because the integral, if you now divide this by 2t, what you get? If you divide by 2t, so 2a C 0 by 2t plus 4 epsilon. So, as t tends to infinity, this part goes to 0, 4, and you remain, it tends to, sorry, it is 2 epsilon. So, it goes to 2 epsilon as t tends to infinity, and epsilon can be as small as possible. So, that means that ergodicity in mean, that condition is satisfied. Okay. So, we normally prefer this condition. And before I conclude, this the other thing is ergodicity in correlation. Here, suppose you have got R lambda as E x t plus lambda x t, that lambda is a lag variable here. So, if you know, if you have any observation x t waveform, you find out this product, again next time you observe the waveform x, find out this product between the samples at t plus lambda and t, okay, and carry out this and average over several observations, which is an ensemble average. So, if your number of observations is higher and higher, finally, this right hand side becomes a good estimate, I mean that ensemble average becomes a good estimate of the actual R lambda, that is actual statistical average. Question is, if I define R t is equal to 1 by 2 t, sorry 1 by, I will take just 3 more minutes. This quantity question is, does R t question limit R t tends to infinity, is it equal to R lambda? If so, I say it is ergodic in correlation also. Okay. Remember one thing, R t is independent of t, because the integral is a function of lambda only. So, R t here is a function of lambda. So, for this to work at all, for this to be valid at all, this R lambda, this expected value should not depend on t. That means the process should be stationary in correlation also, because this expected value of x t plus lambda into x t as written here, it should depend only on lambda and not on t, because if you want R t to be equal to R lambda as t tends to infinity, now R t is an integral where t disappears after integral. So, that means R lambda also should not have any t, which means this expected value should not have any t, it should depend only on lambda, which means it is stationary in correlation. So, that is a primary condition, the process should be stationary in correlation. In that case, when should this be satisfied? Now, you see x t plus lambda into x t, you can call it a process say z lambda t, and therefore, this is again z lambda t. So, obviously, this is equivalent to saying that the process z lambda t is ergodic in mean, because what is if you consider z lambda t, what is r lambda? R lambda is nothing but, so lambda is fixed here. For a particular lambda, you have got a process z lambda t. So, what is r lambda? R lambda is the mean, okay, of z lambda t. And what is this? There is z lambda t plus, this is z lambda t time average from minus t to t. This will become equal to r lambda, provided the ergodicity mean condition on z lambda t are satisfied. Now, we know what are the conditions on the, what are the conditions for the ergodicity in mean of a process. So, if z lambda t is a process which is ergodic in mean, obviously this will be satisfied. Okay, that means if you define C Z Z T1 comma T2 as expected value of Z lambda T1 minus, okay, what is expected value of, just one more minute, Z lambda T, that is expected value of x t plus lambda into x t, and this is our r lambda. Okay, just one more minute, this into z lambda t 2, just one more minute, r lambda. You define this C Z Z T 1 comma T 2, we know what is z lambda T 1, what is z lambda T 2 and all that. Okay. This expected value you carry out, and this is the covariance, then this should satisfy that condition. What is that condition? That 1 by 40 square C Z Z T 1 T 2 d T 1 d T 2 should tend to 0 as t tends to infinity. Okay. That is all for today. So, maybe we will just, I will just touch upon this a little bit in the next class, and then we move to the next topic. Thank you very much.